I'm going to be streaming to YouTube, by the way. In case people want to watch it later. Pues que... Okay, so yeah, everything is working. I think the streaming should be working. No, wait, it's not. Wait a moment. It should be streaming. I mean, streaming case is recording, but okay, now it's working. Never mind. A lot of previous work was assuming like the linear representation hypothesis, where like some like things are represented as directions in some space, in the activation space, and things like sparse autoencoders make this assumption, and also for things like probing and the usual methods where people do steering work. But Good Fire has and there is some other papers that kind of point on this direction in recent 3 years. Well, more last year. That actually like models represent things at least sometimes as vectors, as manifolds, low dimensional manifolds in activation space. Like there are some papers finding curves, or like there was the previous paper we read on the reading group about this from them was like showing manifold steering, where they have some toy examples where they knew there were things that were represented as manifolds, and they found the manifolds and they did the steering along the manifold instead of linearly, and that worked better in some ways. And yeah, this is a new one. I haven't actually read it yet, but we'll go through it. Yeah, I'll go through it also for the people who haven't read it. And if you have some takes, you can also talk whenever you want.
There are some people that believe everything is represented as a linear direction, but these people are trying to show actually it's more complex. There are complex shapes.
Yeah. Also, you don't need to talk on chat. You can also write on the chat if you don't want to talk. I'll try to look at the chat. Okay, so Sparse autoencoders are widely used to extract interpretable features from neural network representations. Yeah, so the process direction. Yeah, that's the thing I was talking about. They just say here that this papers and sparse autoencoders assume things are linear, and there are new papers that many concepts are organized at low dimensional manifolds. Coding continuous geometric relationships. Although we don't know how much this is like, are all concepts manifolds? Are most of them? Are other things linearly presented? I don't know. I think you can probably get some information for all the existing papers. A problem is that I guess I'll talk about it here. That the thing is, they say here that like these are too much questions. Like first, what does it mean for Sparse autoencoders to capture a manifold? And whether characters do somehow. I think there's a thing here that I think that maybe get into where if you are taking linear directions, like you're taking directions as features, you can subdivide the some more complicated manifold in a bunch of points and directions, and that can make it seem like you choose methods that assume linear things and work. But yeah, for the answer so the Sparse Autoencoders can catch manifolds in different ways. Globally, by allocating a compact group of atoms whose linear spans the entire manifold, or locally, by distributing other features that tiles its. Yeah, I think this is the thing I was talking about. That if you are doing normal Sparse Autoencoders or linear prose or whatever, and the actual representation is some manifold, you are going to be tiling the manifold with some linear directions and arbitrarily assign them to different things, even though the actual representation might be some continuous manifold where maybe you represented numbers up some curve and you pick each number as having some direction that happens to match with the correct point in the curve. But you need a lot of features when you could just have some representation of the entire curve and that will work. Empirically, we find that sparse autoencoders automatically cover continuous structure, missing the global subspaces and local solutions in a parameter array and we call dilution. Okay. We see what that's about. This explains why manifold structure rarely visible. And podhosts discovers methods that self-recognize groups. Broadly, also suggests that future representative should treat geometric hertzes not as the basic of Lynch interpretability. Yeah, I think that's what I'm getting from this Good Fire paper. Although I'm kind of waiting for them to actually release a paper, which it sounds like this is not that yet, where they actually make something like sparse autoencoders but with geometric some kind of manifold thing as their features instead of directions. But yeah, they haven't done that yet, but they had said on Twitter that they are working on this.
Alex specifically ask them and they replied soon or something like that.
Yeah. So yeah, they. I mean, it was the obvious thing to do after the previous paper. It doesn't surprise me they were doing. But yeah, they did confirm to me on Twitter that they are actually working on that. They did at least a big post about it.
Yeah, basically.
So okay, so what does this actual paper do? Okay, so this is introduction stuff. Hidden presentation, hidden map. So yeah, so assumption about linear things. Yes, like someone asked if the stream started. Yes, I'm streaming, by the way. Anyway, so is that? Oh, I was not that was that remind me I was not actually streaming
On the stream, yeah,
the screen.
I just noticed.
I fixed it. Yeah, I accidentally changed it earlier because I was not sure the stream was working. But yeah. So I should also remove this so it's better. And maybe zoom a bit because otherwise it sometimes it's hard to see on the stream.
Yes.
Where was I? Yeah, so yeah, this is more introduction. Sparse Autoencoders good, but they have problems, whatever.
Goodfire is applying sparse autoencoders and similar things a lot. That's pretty good.
RPG behind the geometry of neural representation is more indicated than linear representation hypothesis. Yes. So
You should go through some of these papers that are showing different things that are
yeah,
not linear.
maybe at some point we should read some of those. But yeah, I mean, there's maybe some of them well read. It's hard to remember just from this kind of citation where it's just the
Yeah.
name of the authors. But yeah. Yeah, as a matter of interpretation model presentations. First, of course, the activation is more than perceived more geometry model presentation. The key issue is therefore not what the geometry serves, but is organizing a useful interpretive way. Make it for your contributions. Yeah, okay, so I guess that's the question of maybe the sparse autoencoders are taking the wrong assumption that is linear, but by making a lot of features that are some line, they could actually have the representation, the correct representation, right? But that does, yeah. But is that actually like you could maybe find this geometric structures by clustering and that kind of thing on the Sparse encoder features? But I guess a question is that actually the case, or does the sparse autoencoder, like, does the bad assumptions of sparse autoencoders makes, for example, that so that the sparsity uh, moves the model in the wrong direction because it's trying to be sparse in the wrong basis or something like that. Like it's trying to be sparse on tiling some manifolds, and if it we wanted some representation where it's actually uh, where the assumption is the sparse is correct, you will need to talk about manifolds or something. And yeah, and yeah, what problems does this cause if the interpretation actually, at least sometimes, some manifold thing, and we're assuming they are linear? Is that what I think this paper is trying to do? Formalize the problem of cartooning. By the way, at any point, other people can say something or comment or something. I mean, I guess I'll
Is
try.
there like a formal definition for what um, for like a manifold versus something that would be captured under the traditional assumptions of the linear representation hypothesis? Is that
I mean,
defined anywhere in the paper?
we'll see. I haven't, gotten there yet.
Well,
But
manifold is like
yes,
the thing is people usually use this word a bit vaguely in machine learning, but but usually manifold is a space that looks locally Euclidean if you zoom in, but if you zoom out, it's not Euclidean. So like torus, for example, is a or like a case of a manifold, like a
you can
donut,
think
for
of it
example.
as like generalization to more dimensions of like a curve or a surface or something like that.
Yeah. So yeah.
Uh,
So like a
Though,
line.
yeah, they here they're using it kind of vaguely, where it doesn't actually have to be a surface or a curve. Like it can have like some gaps or something, but approximately a manifold is what they're talking about, I think.
Yeah, basically, linear representation hypothesis assumes that everything is a line, which is a special case of a manifold, essentially, where it's like one dimension. Uh, and yeah, you can have instead of lines, you can have curves. And you can have circles instead, which are like curves that are connected. Then you can go into more dimensions where you have planes or like uh, spheres or something,
Yeah.
cubes, for example. So, and the
Yeah,
different features
like
seem to
the
form.
circuits in the grokking paper has a circular feature, right? Something like that.
Yeah, something like that. A lot of other things are maybe better examples are like days of a week are in a circle. So you could say it's on a circle manifold. Um, like here's some examples of some manifolds. Yeah, which is what they basically work on in this paper on. Trying to find these manifold in unsupervised ways from SA features, since both methods right now are just, hey, let's plot it and see it
Do
ourselves and find the
they
manifold ourselves.
do they actually do this or that on the paper? I'm not getting the
Okay,
impression we have all
let's
that yet.
actually see. Maybe you know, maybe I'm misunderstanding.
Okay,
Okay.
so we'll see, but my impression from the stuff I read so far is that this one is not yet their promise unsupervised sparse encoder manifold thing, but this is still yet another paper of formalizing stuff about why that's necessary, why, in what ways the linear manifold, the
Word,
linear sparse encoders are bad, assuming that it's actually represented as a manifold.
we define everything
Ah,
that
okay,
is
yeah,
well
never mind.
motivated by
There
the
is,
Ising
I was wrong. There
modern
is an
physics.
unsupervised discovery of manifold structure section, so maybe there is.
Yeah, okay.
Okay, but towards a primitive confined division problem, okay, so they do have an. Oh, but hmm. We'll see what they do exactly. But it feels like it's a secondary thing, and the paper is mainly about the other stuff, and so that makes me think it's probably not like the method that works for any that's the perfect method that works for any model yet, or like it's maybe has some problem. But we'll see what it says though. Um,
What do you mean? The supervised data is a problem, or?
No, I don't know what it is. It seems weird that this was the thing we actually were most interested in. That wouldn't be the main thing on the paper. Uh,
Okay, I see what you mean. Yeah.
so I'm guessing it's there is some caveat here. Uh,
Mm-hmm.
but we'll see. So static items have personal style manifolds. Okay, that's interesting.
Yeah, hasn't it always been the prevailing theory though that these lower dimensional manifolds exist, just like from the machine learning community in general, right? And then
Well,
even
it's
like
one.
possibly,
Yeah. It is the
yeah,
manifold hypothesis.
right. And then that local linearity just like being the thing that is emphasized on, right, which is the fact that things are locally linear. So presumably that's why even making the linear assumption typically kind of works. And then more on the extreme end, right, you then have folks in topological deep learning, right, which don't make the assumption around distance or direction and just on connectivity, right? And then like that, obsession in that space being like finding where things disconnect. So possibly the fact that even like the manifold hypothesis has holes in it, pun intended. But yeah.
I
Yeah, I've been
think
thinking about that as well.
I
The
think the
holes.
thing on typical machine learning is not talking about feature. I think on Mech Interp, a lot of papers have been assuming that features are I have assuming the linear representation hypothesis, partly just because it was easier more than because they thought it was true and it seemed to work. And I think like often the typical machine learning thing was talking about. I was thinking about this the other day because I think I was a bit confused with this. But it's more talking about manifolds in like the data, in that like the data lies in some low dimensional manifold of
Very true. Yeah.
input
Yeah.
space, and this is about learned features, and I guess they are related.
Yeah.
That if think data lies on some low dimensional manifold, and also that I don't know the outputs are also smooth on that.
Basic. Yeah, it's basically impossible to measure empirically the manifolds in data, as far as I know.
I mean, on
uh,
input space, you should be able to. Like, it's just
uniquely. Yeah.
saying,
Uh,
or not okay, not on text though, because like on text the continuous thing is learn embeddings. But if you are imagining a bunch of like in an image model, you can talk about manifolds in the data.
the dream, as far as I know, is that these models are actually learning the low dimensional manifold, latent
Yeah.
manifold, inside the high dimensional data sets, like that they are actually like properly learning them, which we don't know if that's the case, but I think it's true in a weak degree.
Yeah, I think
As
this
it,
also
yeah.
like becomes what does that even mean in that? Okay, like
Yeah, I don't know how to test that.
okay. So if you are, I think this is because of what low dimensional manifold are you even talking about? Because like okay, if you are talking as like that training data falls into low dimensional manifold in input space, then okay, but that's uh,
Yeah, this is assumed some objective structure in the data that the model is approximating.
no,
Or
but I mean,
not. Yeah.
if you okay, so there can be that structure. Like I think this very like on token space is kind of okay. It's kind of eh, but on
Yeah.
pixel space is just clear that there is if there is some structure, it's just some structure on the space of
Yeah.
possible combination of pixels. So
It,
that's just right.
it's like,
Uh,
yeah, like it's like similar that like a group, like if you make the model learn groups, those groups have explicit objective structure, which you represent as just like which you can represent as just tokens. uh, like so this is like similar, like assuming that the any data like this that we feed into the models have this
but
objective
yeah, the
structure,
thing you
manifold structure.
want the model to learn, like the model needs to output something. Like so, the main thing you want the model to learn is, I mean, maybe you want it to learn the structure of the data, maybe it learns it. Like for example, clearly there is some structure on the relationship between years or whatever. Big runs between days or whatever, and the model learns it because it has these geometric structures. Uh, but I mean, I think it's some. Uh, well, one is the model to output the right thing, and then like maybe learning some structure is useful for that, but it's not, you know, necessarily the case that I guess you can also
Yes,
think.
it is not always the case they learn the structure. So like I don't know, I think the example there is like when you put when you make it learn groups or some other algebraic structure, like it had problems with associativity, for example. um um yeah, in one paper we looked at where you had the toy model where it learned groups. So it doesn't all like they're so guaranteed that gradient descent will learn this structure. Uh,
Mhm.
yeah,
It often does though.
yeah,
But
it often does.
I'm just saying that that like the whole that this kind of becomes under both that first it becomes under specified and you need to be very clear about what exactly like in which space the structure you are talking about is, like is in some vague concept space of the real world or something, or is it just directly on input space? And
Yeah.
the input space is undefined on transformers that are using text input because it is not continuous. I mean, I guess you could do some discrete thing, but it's kind of in the end, it's just using token. It's just using embeddings, and embeddings are learned.
Yeah, some people are talking about structuring a platonic space of ideas, but that's unfalsifiable.
Yeah. I was thinking we were arguing about. I guess I'll talk about later because I kind of let's go back to reading the paper. But I think I have takes. I was thinking on the talking with Claude and thinking out more about the solid stuff, about the curve fitting stuff, and I think I was thinking about it wrong. Understand
We may be diverging.
more what he's talking there, but I'll leave that for after the paper. Good, let's
Yeah.
go back to the actual paper. Uh,
Yeah.
Law reconstruction error. Okay, so going back to the. This suggests.
I like that they use Ising model. Ising model is a very good model.
Wait, sorry.
Specifically, it's a model of ferromagnetism in statistical mechanics.
100% manifolds through metal equations, so atoms that have the crazy detectors. Yes, that's also a secret. It says student ubiquitous in model presentations are likely to be okay. So this is they're saying they have some evidence that this manifold stuff is actually pretty prevalent on the models, only for like the sparse encoder stuff and how they fail. Uh,
Yeah, I think they wrote somewhere, or I've seen somewhere, maybe it's also in this paper, that essays make it more since they are learned to extract linear directions, that and also discretize it and so on, that they can forget, quote unquote, or not properly reconstruct some of the geometry.
yeah.
I think you were talking about something like that, actually.
Yeah.
Yeah.
Yeah, I was also more about here. I think they are saying that so far we have evidence from previous paper that there are some representations of some concepts that are manifolds, but we don't. That doesn't tell us what percent of features are manifolds. I think they're saying it's actually a lot, and we'll see why they claim by it. But I think it's something about like sparse autoencoders. They did some testing on sparse autoencoders and find that they fail in some way that they will expect if there is a lot of manifolds. But we'll see what the actually says. Okay.
Maybe hot take is that everything is actually a manifold, and there's no such a thing as a feature that's a perfect line. Like every line is
Could
a
be
bit broken.
It could
Yeah,
be
it's always approximation.
approximately
Yeah.
direction.
Yeah.
Well, I mean, obviously, it's never exactly a direction. There is some wiggle room. But
Take that linear representation hypothesis, enjoy it. I'm making fun.
but
Yeah.
I don't know. I will see. The same we will present showing language models. Many real codes fast the structure can give us multivariates on some rates. Yes, I mean not all of them. I wonder, are there cases where the thing is not uh yeah, I wonder if there is if there is some concept that doesn't that seems like it should be discrete, but there is still some manifold. Probably don't have those, but I guess we wouldn't know to look for them. Uh,
Yeah, maybe you have to sometimes jump if something is very discrete category instead of linear linear interpolation. Linear or like not instead of continuous steering, basically you have to like add like 10.
Okay,
Otherwise it
so
doesn't work.
they
It's
take
not
numbers
reality.
where the concept was continuously varied. Yeah, I this is the thing where they take numbers where concept continuously varied, but you should also look at random domains too. Like maybe they are just doing like finding manifolds because they are looking for the places where it's more likely that there are manifolds, and maybe there's a lot of other features that are not manifolds because they don't have some concept that can continuously vary. Uh, yeah. The PCA and they see this kind of curve nonlinear geometries, concepts characterized in prior work, like Dio's the weak. They say new ones, but wasn't the colors already a thing though? Like it's on the or it's only or is the colors new from this one? I'm not sure.
Maybe here they also have lightness dimension or something.
Oh yeah.
And spatial banners, yeah. Maybe it's more complex colors than the before.
We see distance and neighborhoods called semantic similarity. Nearly points concept to similar meanings. Okay. To emphasize this resource further and highlight more strongly the disparity between these manifolds use the scope of linear representation hypothesis, we showcase that these manifolds are not merely geometrical artifacts but are functionally relevant by measuring the effect of model behavior. Okay. I think that we can still allow the manifolds by steering between prototypical centroids and the smoothly interpolated between these points. Does that depend on the ordinary variable? That the border output changes smoothly and predictably along these interpolations. This indicates the manifold structure is not only present in the representation but also casually influences constant behavior. Yeah. So it's kind of similar to the other paper where they also they take the model and they do and you know they do interventions by they do manifold steering like the other paper, the manifold steering paper, where they steer by moving, adding vectors moving through the different points on the of the manifold, and that changes the output smoothly. As the source is causal. Is another example of Mech Interp people trying testing causality, like what the guy in the machine learning thread talk you were arguing with says.
Wait. Well, these people have some other arguments, but let's not go in that rabbit hole. He thinks this is not real causality. Okay.
Okay. Okay, I see.
Because reason. I mean, I think I partially understand, but yeah, there's
To
some reasons.
concretize what it means to successfully capture manifolds identified from off-the-shelf retainers LMs using protocols, files and arrays and extraction that extends linear representations concepts with multidimensional non-linear curve geometries. Aha, yeah. IT
Multi-dimensional
measures
non-linear
manifolds.
curve geometries. That's a very good word. I mean, I'm saving that in my brain.
Set of words.
Yeah.
We are not making a normative class that never satisfy this model or representations. Instead, our goal is to make concrete scenario where we can rigorously define cybernetics and the specificity of the self models. Okay, so they are trying to. So they have this linear representation hypothesis, and this consists a ring activation space. A single activation is created by a coefficient. Aha. the geometric structure identified, which says that this is a special case of a richer phenomenon with which constants value continues over large dimensional structures. The following can be this the previous similar words. Okay. Probably not that word for like the to get to. We're going to spend too much time getting too far into the specific math. If someone wants to, they can go through it and maybe explain it, or if someone has already looked through it, we can explain it. Otherwise, I think we
Yeah,
kind
I
of skip
definitely
it.
want to, but it will take more time.
Yeah. So for now, let's just kind of skip it and continue. So yeah, they. To lie that is for the corner. A small fixed group of atoms spans a substance containing it. The encoder consists groups for every input from the manifold. Okay. That makes sense. So they are
Additive
trying.
mixture of manifolds.
Yeah,
Yeah.
this is about like if you have a sparse encoder with lines, it's like trying to say, does this recover the manifold by does the manifold have enough lines? Okay, so there is here a bunch of regiments. First, like we do this thing, you do this thing where you take the manifold and have a bunch of points that are each one is a feature. Like for example, if this is the number, you can get a Sparse encoder that like has a feature for each number, and then this mess. And
Yeah.
there is this also this compact capture where you have some feature for each of the dimensions of manifold, and you are kind of capturing it. Do you see this? Or I think on anthropic stuff, like on the anthropic paper
Line
of
breaking.
the no, not the line breaking. I mean, the line breaking show also was talking about this, but I mean, there was the example about addition on the anthropic paper about graph. What is the name? I'm missing the name right now.
Geology of LLMs.
Yes, that one. We were doing attribution graphs. That's the name. So they were doing
Yes.
attribution graphs, and I think they were implicitly accidentally doing something like this, where one of the features, like I think numbers there are also probably represented as some curve like this, and one of the features was something like the number is mod 8 is mod 10 is 8 or whatever, and that is a feature that is basically a line here. Like it's one. If you imagine a D2 here, and the numbers are on the circle, and it comes around every time numbers, like this direction is pointing towards the numbers that is most activated by numbers who are most whatever fits here and here, right?
Yeah,
So
like you said that you think that it's on a shape like there's Max Tegmark paper that just explicitly that numbers in LRs are presented as a generalized helix.
yes,
So this is a helix. Yeah.
yeah. So yeah, it's a helix. But the activation graphs are from Sparse encoders, so I think it is doing this. Like it has the activation graph has like a few features, and one of them is the like the number mod 10. I think that's what will be here D1, and another one is like the number mod the first digit, which I think is D2, right? So like you have a bunch of features that if you use person calls are constructed, they sound like they are some weird trigonometry stuff, but they are actually just trying to hit this spiral thing. I think it's what's going on, but I don't know. I just heavily suspect it.
Okay, can you repeat your point?
I think you have to get some features when you do activation graphs on arithmetic that are actually just pointing towards the model actually represents the number with the numbers as a curve like this, as
Oh
a
yeah,
spiral, like in the Tegmar
like
paper.
yeah, like as far as I know, this is how mostly the shapes were discovered. You just sample a lot, then you do this dimension reduction or PCA or etc.
Yeah,
And
but I'm
you
saying
see,
that
oh, it's a
the
shape. Now let's formalize it.
the sparse autoencoder from the biology of large language models is actually capturing something. Is like doing something like the
Oh,
compact capture thing here, because where the one of the features is like the number mod whatever. Another feature is the number mod 10. No, not the mod 10, the like the
right.
second digit.
Uh, yeah. Like because you see the periodic patterns stuff. Yeah. I think
Yeah.
that's the case. Like, it's represented as this manifold, and the different features that just curve different subsets of the manifold in different dimensional ways.
Yeah. Anyway, going back to the paper. Uh, they were speaking. The features that Feucht decoded the relationship was low dimensional
But
detector for them.
like at the same time, what might be the case that like there may be multiple of those manifolds for numbers because the model fractured it or something like that.
Yeah, I mean,
Um,
and I think that case was a manifold for addition specifically. I think. It doesn't necessarily
mhm.
use the same representation for other things.
And
Uh,
sometimes the models reuse like some of these circuits when
yeah,
they
you should
shouldn't.
expect them to reuse them, but yeah,
Yeah,
but maybe
like
that is not
even
always.
for even like for modulo 12, it's reusing a base 10 calculator in Llama because there's just so much more data in base 10, and that's how it reused the parameters apparently.
Oh,
Yeah.
where is that from? That
This
seems
is one
interesting.
good fire paper. Did we read? I think we did read it. I'm not sure. No, we didn't actually. I just read it on my. Okay. Yeah, this is one good fire paper. It that's also about finding a more general like calculator where like when the model wanted to do some modular arithmetic with months, it literally like first converted it internally into base 10 arithmetic, did the arithmetic, then converted it back to the modulo 12 space,
Oh,
because
you
why not?
should put it
And
somewhere
as
because
a
that seems
yeah,
interesting.
and as a result, you have accuracy loss. But my hypothesis, or I think they also say that in the paper, is that like it is just useful to reuse it because finite parameters, finite data,
Yeah.
finite time, etc., etc.
I mean, it's just
Yeah,
not about number of
compression.
parameters. It's more about the general pull towards compression for a bunch of reasons about the shape of the loss landscape and all that, and also the regularization and yeah.
Yeah. Definitely. Yeah, this one.
Uh,
Yeah, modular tensor module to calculate stuff that's living in module 12. Like this is so stupid. uh,
yeah. So
yeah.
here they are separating.
What does the figure with the icing pairings mean?
Uh, I'm not sure what their map is exactly, but I think model is a model of ferromagnetism statistical calculate. So uh, the discrete there's like discrete variables that represent the magnetic dipole moments of atomic spins in the graph in the lattice, and they interact.
And
I
we
think
can
this was
quickly go look at that.
this like the guy who got Nobel for machine learn for AI. The he he got it because like the very I, Hopfield networks, I think, are based on the Ising model, which are like
Yes, Hopfield
precursors
networks
to
and Boltzmann as well.
yeah. So I'm interested to see the mapping they have here, which I don't know yet how exactly they map it.
Yeah, let's get to that. First, okay, so first, here they're talking about three things, which they have like tiling versus capture. They have two types of tiling, which has chattering, where you just have a direction for each different for the different yeah features manufactured by chatting in subparts and features of anti-correlated occurrences. Compact controls simple features jointly reconstruct manifold with activity, resulting in positive couples for the subsport. Deletions occur when many redundant atoms activate the tile manifold, but with feature sets of mixed selectivity. Okay, so you have. Yeah, I'm not sure I completely understand the difference between delusion and shattering right now, but okay. Uh, by the way, does anyone else want to say something? Because I've been talking a lot, mostly.
I think what they mean by mixed selectivity is that the features are sometimes positively correlated and sometimes negatively correlated. Um,
Mm,
so it must mean that, because like in the case of shattered tiling, they say that the features are anti-correlated, right? So
mm,
this is probably kind of like what they mention in toy models of superposition from Anthropic,
mm.
maybe.
I'm gonna check. Uh,
Okay, so
when many
there's
redundant atoms activate the tile manifold, but which feature sets of mixed selectivity? Ah, okay, I see. Yeah, it's mixed. Yeah, that makes sense because the Ising pairings are also mixed.
I have this theorem that I will have to read all of the definitions to understand, but it says something about how the if this person code achieves reconstruction error of certain amount, then there is a sparse decoder over the captures the manifold at some precision. Okay. I guess they explain it better here with less math. Essentially, when reconstruction are slow enough, the sparsity regimen is aligned with the ambient dimension of M, and the
The
dictionary is in
ambient dimension of the manifold is the space where the manifold is embedded.
yeah. So, what does it mean for the sparsity regimen to be aligned with the ambient dimension of the manifold? Is my question here. Because they also talk
I'm not
here
sure if I understand it properly, but my
about features aligning
since
with it.
yeah, since I would have to go through the details, but my understanding is that there is like some like ground truth manifold dimension, and if the reconstruction loss is low enough, then the the sparse autoencoders just capture the dimension of the actual manifold. But maybe they're saying slightly something else here. Does it say ambient manifold dimension? How do they define sparsity regime?
I get here they share something clear. They talk about this where the features align with the
Oh,
ambient space of manifold. So you can also like talk about the features. I mean the sparsity regime. I assume like it's talking about the where the model is sparse on, which is on features. Uh, like it's trying to uh, like okay, I think how it mean. If you have your features are aligned with if the manifold is aligned with the features, uh, you can uh, capture it with few features, so the sparsity is aligned with the features is maybe what they're talking about. But yeah, I will have to read the whole thing to that, and let's really have time to do that. If anyone has read that and like has better explanation of this, like feel free to just talk and say it or write it on the chat.
I just want to say it's nice that when they start the math, they start talking about the notation, so that people, there's more papers to do that basically.
Yeah,
But
I mean, we can read that later, but like for I feel like people here may be more. I'm up for
yeah,
like trying to figure
I'm
out the math later, but I want to get through. I think there are more people who are more interested in like reading, like
yeah,
getting the gist of the paper and all that. So we'll first do that, and later we can start going through the maths. And if people are bored by that, they can leave by then.
yeah.
uh,
I'm gonna go
okay.
through the math right now anyway. But yeah,
Yeah, feel free to do that while I'll keep looking at the more. Yeah, okay, number
yes.
of atoms allocated to a manifold. Uh, when the number of atoms allocated to a manifold extends its same dimension, the Sparse Autoencoders nos controls to reduce a fixed group and might assign different atoms to different regions of M. Okay.
Mhm.
So yeah, so basically where there are where you have more features
Right.
for a manifold that there are the ambient dimension. Why the ambient dimension? Because well,
Of the
yeah, I guess it
manifold
makes
because
sense
the
because
features. Yeah, I think they just mean the dimension of the manifold.
right,
Like
because the ambient
the
dimension of the manifold is the number of if you are trying to do compact capture like this, you need like one feature for each ambient dimension, right?
uh
Yes, I think
yeah.
that's exactly what it means. So I guess what they're trying to say is that all the features are not automatically able to um, do to like capture the manifold, and that it's a precondition for the manifold capture, I
Yeah,
guess.
like the ideal case is this when the model like this manifold has like 3 dimensions and you just have 3 features for it. And if you have more, you are going to have shattering or delusion, right?
No, and also when it's like curved or something, then it yeah. Since I say features are linear, then you just have to shatter it.
No,
As
but
far as I
even
know.
if the features are linear, you can still represent the curve as a combination of features.
Okay, I see what you mean. Yeah.
Like on the capture thing here, like in the compass capture here, you can perfectly represent the curve by just having one feature that represents
Ah,
one
right.
direction on the curve, another that represents another direction on the curve, another that represents the direction curve. But the problem is if you have.
But shouldn't it be free? Okay, that's the ambient thing. Okay, I think I see it now. It should be free. Yo, it is free. I see. Yeah, there's D free. I didn't see it. Yeah, okay. Yeah, that makes sense.
Diagonal
You
zero in
you
figure 3.
yeah.
Uh, Diagonal zero
Diagonal
figure
zero
3.
in figure 3 should be right.
It's me
Uh,
on. Okay, so this is listen firing. So no, because wait, no. Mm. Wait, so what does this? I wasn't paying that much attention to that. What does this graph mean exactly? Is the question. Uh, right. This is using partner pairings, which is they probably spread it somewhere here, but like hmm. So it's have two vectors, and 3 is 1 is 1, and 2 2 2 2 2 is like the diagonal is 0, but the others are high, and here, and there is +1 -1. Yeah, I just have no idea what this means. If you understand it, Saki, maybe you can explain it. You meant this
I
thing.
thought that was the correlation matrix.
Oh,
Like
maybe
if
it
you
is, yeah.
No, well,
Hmm?
maybe. Like in the I Sigma they interact.
like if you increase d1, then d2 decreases, like in a circle. If you increase x, then y decreases. So that's negative correlation.
Yeah, so D1 should be correlated with the self, right?
Yeah. So yeah, I don't understand why. Yeah.
I think there's some things about in the middle of the matrix. Like they usually, I feel like that's the thing that people do when
yeah, maybe
visualizing like these correlation matrices.
yeah, it could be. That's a good point. Okay. Synthetic validation for manifold capture. So the construct they have a benchmark. I mean, yeah. So this is a. This is plus. So this is a bunch. This is a bunch of things. So they have this. So they have this synthetic data, where they have so many faults on the data. I'm assuming. Yeah. As part of me is not manifolds embedding some automations. And I'm guessing they are trying to get to test something Sparse Autoencoders on this. Yeah. Let's see switch those. Sparsity. Per manifold breakdown sweep then the. Yeah, I guess how I wonder how much. I think there's other recent papers from Wildfire do this. Like how much you can go through other papers about ways that sparse encoders fail, and things like features being feature absorption, all that, and related to this the manifold stuff, and like how things change with sparsity and all that. This spiral drives the sparse encoders through three arguments. Although K, atoms are broadly shared, and the manifold is shattered at unrelated groups.
Oh, this is good.
Hmm?
Yeah, I just wanna say this is good. That like how they model increasing sparsity. Like this was my hype. I think it's maybe obvious. I don't know. Like if uh it was seen from some graphs that from Anthropic and others. Like as you increase sparsity, you get much more granular features. So when it comes to modeling
Yeah.
this manifold, you get much more granular
Yeah,
parts
that
of the
was the
manifold
thinking. Like
as
there was
distinct
all
features.
those preview results about that kind of thing. I wonder how they translate into the manifold stuff.
Yeah. So if you have a lot, like a very big SAE dimensions, and then the manifold is just shattered on all the different parts, uh, uh, like templed. And if you force it to use much less dimensions, then it will it will have more I don't know, feature for like the compact capture basically instead of shattering. I'm not sure that's general rule. Maybe like as in
No.
I'm not sure if like you still also get features for the compact factor capture at the same time shattering as well. It seems like you do more shattering. You see more shattering from the SAE features I've seen when they are like plotted across the different sparsity regimes, basically. Oh, sparsity regime is how many dimensions, I guess. That makes sense. Yeah, because you have infinite parameter regime first. Okay, that would make sense terminologically. Yeah.
Also, does anyone else want to say something? Because I think I saw someone
There's something in
unmute
the
for
chat.
a bit. Oh, nice. Yeah, I'm trying to think of the compact capture as some vector space with some no minimum number of features needed to expand the vector space. Ah,
Yeah, I think that's true.
yeah, that makes sense. Shattering is when you have more basic features than the minimal, while dilution you have a lot of features but don't capture it entirely. Yeah,
Oh,
I think the compact thing is true. I'm not sure for the. I'm not sure. I don't understand completely yet, like the difference between sputtering and shattering
yeah,
versus
like
dilution.
the okay, if I understand correctly, it's like you basically you don't have enough. You just don't have enough power to get the whole manifold. So you dilute and just get subset of it. Many redundant atoms activate
No,
the
like
entire manifold,
both
but with
in both
features like
shattering and
portals.
dilution, you
Mm.
have more features than you did.
Okay. Oh, maybe it's like because it's mixed activity, then I just have to go through the map step by step
Yeah,
instead of
we
trying to
have to move
intuit
to
it.
math. Okay,
Okay,
it says.
but like another like that customize that.
Okay,
Okay, so you first go in one direction, then in a
okay, so
different
here they're
direction,
explaining
and jump around.
many the delusion as many redundant atoms fire per point and individual atoms loss specifically. Yeah, so there are more features than points, I
Oh,
guess.
this is feature duplication.
Yeah,
Many
I think
redundant atoms fire per point.
that's true. Yeah. Uh,
Hey,
And
can
loot
someone
specificity.
clarify what K means? What does K mean?
oh, on
Uh,
this graph they are talking about case sparsity.
yeah,
Like, yeah,
the
here it says dictionary width and sparsity K4.
which I think like is I'm not sure if this is how they calculate it here. Like the dimensions of the SAEs is the
It
dictionary
might be
times
a
the
top
sparsity.
KSA and they just,
Yeah,
put it K at 4. Uh, because like the dimension, no, the dimensions of the SAE I think is the maybe the dictionary width here. Because I mean maybe spanning. Yeah, I don't know. Uh, Moving outside, this is interesting, I think. Okay, so the capture regime manifold structure can be recovered post hoc. Firewise easy model can, which I'm not sure exactly what it is. We'll see. Maybe I think from the thing we said before, maybe it's like related to correlation. Coders, yes, a coupling matrix. Yeah, that sounds like it's actually just fancy correlations. Whose block diagonal structure aligns with the ground truth manifold partition. Decode through the recovered atoms. I think yeah, this is related to the thing when you can get curves from from correlation matrix related to that paper Do you remember, Bonnie, the math paper that was talking about
Yes,
how? Yeah. So I think this is related to that.
Decoding through recovered atom groups. Faithfully reconstructs the topology and geometry of all manifold types without supervision.
Like if you have a bunch of features, even if there is shattering or dilution, if you have a bunch of features and you can get for the numbers, for example, you can get back the shape from the correlation matrix.
Right. Yeah, something like that was done in the paper that you mentioned. Maybe that's what they're doing here, yeah?
Also,
And why
yeah,
cannot
this
you do
is
this for activations? Why do you have to do it just for assay features? How is this method
because
general to activations?
because you will need correlations between all possible activations, and that seems like it.
Oh, understandable.
Right? Like if you have all of the, I mean, you could. What does like you don't have correlation between like each activation only happens once, so you can't do
Yeah,
correlation between them.
you with assay. Ooh, actually, what if you did this assay thing? Okay. Yeah, that's stupid.
Circles, weird. Okay, yeah, so there's a bunch of these are very small graphs, but okay. Yeah, so this is the graph for this thing is capture, and other thing is the sparsity. Yeah, it's top k from the k. And they show for. I'm not sure what n here is, but maybe it's the dimension of the circle, but or no, yeah, I'm not sure what n is. No.
Let me see the graph.
N2 dims, which is the number of dimensions on the circle, which makes sense. But yeah, I know. Or maybe it's related to the capture.
This is the A. Stopwise
This
capture
is a
has the
yeah.
sparsity sweet spot. I think it's sparsity. No?
No, sparsity is the x-axis.
Oh,
But yeah, I guess it doesn't
what
matter. I
is
think
it
the main
called?
thing is the bright line, and I
Texture?
don't know what the other things are. And yeah, aggregate. Also, yeah, if you aggregate, you get this one.
Capture R3. I guess it means how much you capture R3. As in
Yeah, I think the super stealthy
accuracy.
ship is correct. Like you can kind of reconstruct it in all cases, but in the capture case you just have one, like the minimum amount of dimensions. You just have one dimension for each dimension on the manifold, and everything is nice. You just at each point is some linear combination of each feature. On the shattering case, you have a bunch of latents for each point, and the dilution cases when you have even more features, and you just have more than one feature for each position on the graph, which I think you need normally that just you have very you don't have a lot of sparsity, and you are you know normally Sparse Autoencoders are trying to not do that. They're trying to have less features and not have more than one feature for the same thing. Okay, so yeah, this thing here is they have this capture score, and captures happen more with this sparsity, and then those goes down.
Someone in the chat, by the way, try to wrote.
Yeah, I was talking about that.
Okay, I see.
Yeah, I think it's right, more or less. Okay, so
Yeah, it makes sense. It's like feature duplication.
so there is a bunch of okay. So here, what do they say about this? So each atom with a set, yeah, this because neuroscience. Oh, this is interesting. Oh, there is some neuroscience thing, wherein neurons are argued to be sensitive to
Receptive.
different variants of a concept, covering overall geometry by the population code. I mean, that sounds like actually the neurons are the representation in neurons are also some manifold too, and the neuroscience people are just being confused by looking at each neuron individually. The way you would also be confused if you were looking at each neuron individually.
They also they also look at the aggregates and so on. There's also sparse codings. Yeah, like
Yeah.
neural manifolds are fake in their sense. Yeah.
In line with this later, we call it phenomenon tiling, localizes files with overlap and support. Yes, continues to be. We need to look into neuroscience for Mech Interp.
I think I'm arguing that actually. I think a lot of Mech Interp is actually rediscovering concepts that exist in neuroscience. Not everything, but all of it.
Yeah.
Maybe it may be the case also because neuroscience people are coming into Mech Interp and then showing the method.
Yeah, as we showing things. I mean, I think a lot of is both in neuroscience and here. You have some big amount of things that are doing some combination, maybe even like linear combinations to with some non-linearities to do stuff, and you're trying to represent data with that, and yeah, so you are going to see a lot of the same phenomenon. Like you're going to have things with superposition, all that. Even like
Yeah,
because
like
a lot of things are geometry, and you should expect the same thing to happen on the other thing because also geometry, right?
I think in the original essays paper from Anthropic they say that there is a corresponding method in neuroscience to the essays
Yeah.
to sparse coding. I don't know how it's called. It has a different name. Also, it's used in signal processing. Diction
Yeah.
learning is used for EEG. I just found it.
Yes, you should expect that to happen because it is just a lot of this stuff are general facts about like you know the geometry of having represented thing as combination for a lot of things like neuron activations.
Yeah.
If you want to do that, have something that does that efficiently, you are going to see the same kind of shapes and so on because they are just the efficient way of representing things on that space. I mean, if the actual representation is but a different learning algorithm or whatever. Uh,
Yeah.
okay, so yeah, so they have talk about tiling, and inside tiling they have shattering and dilution. Where the difference, as we said a bunch of times here, is that in shattering they have a set of nearly disjoint, they have a set of nearly disjoint features or whatever atoms partition the manifold, and dilution when there is overlap. And yeah, regardless of whether Sparse encoding dimension, the group of the code dimensions of a manifold is unknown and will be discovered from the codes alone. Yeah. To this end, one must use coactivation statistics. Atoms that usually represent a manifold fire together or in a small succession about inputs on M. Yes, that's the thing we were talking about. Raw coactivation, of course, conforms to distinct sources of statistics. Structural coactivation, yeah, basically because they are, which is, yeah, atoms span a tile the same manifold, yeah, so that you have two atoms like sampling their similar position tiling some manifold, and so when you move through it, you start, when one is active, it's more likely that the other is active because they are on the same, like they're on the same line or something, and you're moving through the line that they are on the same manifolding. And correlation and co-occurrence. Constantly of data. So yeah, where there is also the case where they are not on the same manifold at all, or like they are completely different directions in activation space, but it just happens when the model activates one feature, it tends to activate the other for reasons they are correlated. It's also dominated by atoms that fire universally with activates everything with carry from manifold information. Okay, yeah, that makes sense. This is also atoms that fire universally are like features that fire universally are a problem with for sparse encoders too. Because if you are trying to do a sparsity, you'll have problems with features that are always there because either you want to always represent them or like I mean, you can not have a feature for them and just make the decoder always write them or something. But they could be that they doesn't always fire, it just fires most of the time. And yeah, there was some papers about this, about like high frequency features on sparse encoders. I think parents and
High
yeah,
frequency sparse autoencoder.
high frequency features in sparse encoders. There
Oh,
was a
okay.
paper, that we read on that.
I mean, I would expect like I don't know English to be one high frequency feature. Well, it's
yes,
not
that's
because
an example. If
yeah.
there is some English feature and it's activated most of the time, uh, like that generates problems with like the learning. I can't remember exactly what the details were of that, but yeah, like the learning expression encoders where it wants to do a sparsity and only represent certain features, but it could if always activate the English feature. But then if it, let's say it has top K, there's already one less feature, and has tech fail 4, there's already one of 4 features that it has to remove. Maybe instead it wants to, if only says English text, it will want to do something like put English activations in all things that are correlated with being English text instead of making it a feature or something. Uh,
Spurious correlations. Wow, this is cool. They try to look at spurious. Yeah. By the way, this is one of the critiques of the causality people is that spurious correlations and confounds everywhere. And this paper specifically talks about confounds and spurious correlations. Chevsky's, I like it. Anyway, yeah, they also have other critiques. I think we can learn a lot from the causality people, by the way, generally.
okay. I mean, I think.
I mean the mathematical causality people, not the philosophy. Okay, maybe some philosophy causality people as well, but honestly, I have very much low, good experience with that. I don't know. Maybe I'm just not open-minded
I mean,
enough
I
or
think.
something.
I mean, yeah, because this it's true that but yeah, I don't know. People are already know about causality and like the. I feel like that a lot of papers already are trying different causal
Yeah,
interventions to
definitely.
see.
Like
But
if
yeah,
you want, we can read this paper that I linked, which is the most quote-unquote causal paper that I could find. Um, so which criticizes a lot of Mech Interp methods at the same time. It's basically saying causal abstraction theoretical foundations for Mech Interp. So it's like saying this is how you do causality properly.
maybe I'm
Yeah,
mistaken. But did we read this paper or a similar one?
I
Maybe.
don't think so,
Let's
or
see.
maybe a long time ago. I don't
It's
know when
possible.
I wasn't here.
Anyway, going back to this, I think paintings and regions of manufacturing. I'm curious what's icing. I get that is some way of measuring correlations by now by context, but I'm not sure exactly what it is.
Wait. I sometimes go through the icing a
Oh,
lot.
like it's the
And then I forget it.
It's the
Yes, it's the
ferromagnetic
ferromagnetic thing, and it shows how like the different spins interact with each other. So it like makes them line up in positive or negative direction, depending on the definitions.
So yeah, but
So
how
like it can get to some local minima, and from that the first like Hebbian, I mean not Hebbian, the
like what's
uh,
adding like
other
in part
network.
what size like how does it work here? Because it seems like it's working as some kind of way of talking about correlation between sparse encoder features, right? But like, how does that work and what does has
Yeah,
to do
I don't
with
know. I
the
have to go
physics?
step by step through. I have to go step by step through the map. I will start going through the map, and then I start
Okay.
explaining to you.
Like so far,
As we go through the map.
I'm like the
But
main
yeah,
thing I'm confused is why what does this thing add that you wouldn't get by doing all the same stuff but like just correlation a correlation matrix between features. Maybe
I
it's
think
related to
maybe they
the
okay. I don't know yet exactly, but maybe they do it because if you cast it and I think this frame, then you by for free get some mathematical results from the other field.
maybe.
That is my hypothesis why they do
We'll
it.
see.
That is usually the reason why they cast it to a different domain through some isomorphism or something. At least if they do that. Yeah.
After condition of rest population. Okay, so it says dependencies that arise from atoms going to represent a manifold. Others that fail frequently allows inputs are inspired by script with couplings. With it correlation. Oh, it seems like they do get some nice properties from this, but okay. So indirect correlations in this proposition are factored out by construction. As a result, okay, they are basically Burnie. They are basically answering my question here that for a bunch of that it has some nice properties that I don't understand why because I don't understand how icing works, but whatever. Like where it's somehow it avoids counting superposition and
Are factored by
are
construction. Hmm.
for some reason that I don't understand by construction, and also atoms that are features that are high frequency features have some large whatever number and then weak couplings so you can separate them. So yeah, they're saying that for these reasons it's better than just doing correlation. So basically, they're saying that all of the problems that they mentioned before, except maybe the correlational co-occurrence, are solved by just using this physics thing. Yeah, no idea why. Anyway, if someone thinks I'm getting something wrong, just tell me. I'm just kind of trying to figure out as I go and saying what my current idea is. But like often when I'm reading these papers, I'm wrong for a bit and then realize I was think more about it and realize I was wrong and then I'm wrong again and then I change my mind again and I end up only understanding some things until like the end of the paper, if ever. uh, Also, if you're interested in some specific part of the paper, we can briefly skip to it and read it. But yeah. The science corresponding is Sparse Autoencoders. In the tiling regimen, atoms specialize in distinct relations of the manifold relative to other, leaders to negative copies of the code multiplication.
Like in
Illusion,
the spin modeler, yeah, I don't see the correspondence yet, but in the spin model, like each spin tries to agree with the spins next to it. So like if you have 1 and -1 next to each other, then they will both like one will go down, one will go up, and eventually they might like agree.
Also, by the
So
way,
in the
yeah.
end,
So this thing is not correlations; it's this icing thing, which is kind of like correlations, but it's not
yeah,
exactly correlations, and maybe that's why the actual reason why the diagonal is white, but no idea.
yeah. And like the idea there is like that the aligned neighbor lower the energy. Uh, and like there is no rule that depending on how you start the whole lattice of spins that try to align with each other, there is no rule that it will eventually all like go to some local minima where everyone lines up globally basically. So it can just do some oscillation or something infinitely. But I don't know the mapping of this paper yet. I have to go through it in more detail.
Okay. Yeah. So. The tiling regimen, atoms in the scattering regimen. Yeah. So quantity consists of the inputs, positive couplings within the group. The tiling regimens leading to strong negative couplings that cause most of the exclusions. Okay, yeah, this is again the thing with the icing on the previous figure. Fusion regimens a mixture of positive and negative interactions. Okay, so the basic thing is they say they claim they can you can separate the capture and the two kinds of tiling depending on what the how negative or positive the couplings are. I mean, the real network is going to be a mess with some parts and some things are going to be negative, some are going to be positive. Yeah. Uh, this is a relative interaction matrix. By identifying manifolds through metric similar correlations, we can recover them as communities of atoms with strong pairwise interactions. Irrespective of whether those interactions are cooperative or inhibitory. Okay, that makes sense. Common structure depends in feature activations, which operates. Okay, so I guess this may be related to the things where they talk about unsupervised finding of manifolds. Maybe it's looking at unsupervised frames from sparse encoders, but it's not yet from training something that serves sparse encoders, but with manifolds. Maybe that's a separate thing. I don't know. Okay, yeah, that's nice. So you have the Sparse encoders from correlations, but in this physics framing, you can find manifolds on those. On the from the correlations between activations of different features. I guess this
Yeah.
still has the confound of the of correlations of correlations that are not about structure, but you can
Curious
probably
correlations.
separate that out though.
Like what like yeah like there there's an architecture called causal JEPA by Lacoon, and one critique of the causality people is that anything this architecture can learn is a spurious correlation. Well, yeah, might be more general for ML.
I feel like the general. I think the causality people are that say that the ML can only learn correlations are wrong, and I have takes on why. But
No, no, no. It is not that they only. Well, okay, some people say that, but like some people that are more nuanced say that like the models struggle to like separate spurious correlations and actual correlation and like actual correlations and causal relations and so on. At the same time, I think the same is for humans, but that's I think we can build architectures that actually can separate it better than humans in superhuman way. Okay.
I mean, I think it's just a question of. But I won't get into this right now because I kind of want to finish the paper. But I think it's just a question of finding inductive biases and finding simple explanations of the training data and how
Yeah, that
you
might
can
be
see
case.
how, like, if you think about Solomonov induction, it finds the correct causality even though it's only getting the data, and I feel there is some kind of people who have philosophical views that are broken by that because they will think that you can only, if you're only seeing, I don't know, combinations of symbols or whatever, and then you can't get the true causality because you're not doing causal interventions or whatever. But that's not true, and the answer is about how you can actually get causality from correlations with some inductive bias, but let's ignore that and go back to the paper. Also, Usagi posted something that with a crowd explanation of the of something. Let me see on the chat. A concrete example: 3 features: hot weather, winter, hot chocolate. Will be correlated on the data. Don't directly interact. Okay, yeah. So cold weather and hot chocolate pair together a lot. Yeah. Common case. Correlation has high value. The C model will be near zero coverage because of the condition D3 on D1 and D2 is 3 independent. Ah, okay. I still feel like I will need to understand how the icing model works to understand why is that the case. But yeah, I understand that this also seems related to the correlations versus causation stuff, right? I mean the thing that if you read the thing that Husagi posted on the chat.
Okay, I see. Claude explains. Yeah, I'm gonna check.
It is related to how, like, you can see the causality as being a way, efficient way to talk about the structure of conditional correlations.
For example, imagine 3 features.
Anyway, so they have these toy models. Anyway, going back to this. So they do the toy model. There was on a previous figure, and this is the figure for stuff.
That's the condition.
We already saw the figure for stuff. The space capture has a sparsity spots, increased sparsity drives sparse colors to the circles of the arguments. You said capture remnants for first cover post hoc. Okay. Yes, that's nice, but that's on some synthetic data where they just have some actual manifold and they just try to reconstruct it. The question is, what happens on real models? Okay. So that's what they are doing now. So we train 5 Sparse Autoencoders architectures, standard L, Merullo, top K, batch 2K, Matryoshka, with a bunch of different parameters. Sparse Autoencoders do not enable compact capture. They apply the same structure to programs for each manifold. We regularly set announced by pseudo balance. But I never actually look at how they actually test. Think this how they test that. But okay, a measure reconstruction quality as a function of support size. Fixing shows the result average across manifolds and architectures. Versus sprint with the number of resident features. Produce at the support price well beyond this manifold and dimensions. Yeah. This indicates that Sparse Autoencoders do not allocate a component attributes corresponding context to the manifold. I mean, is that? But are there not some manifolds where they do that though?
They do not allocate compact atoms per the manifold.
Like they are averaging about manifolds and architectures, but it seems plausible to me that like the actual thing is more like it's capturing some manifolds and not capturing at all others and so on.
Yeah.
Also, they're talking about manifolds, but do they? How they know which manifolds to pick? Are they? Okay, we'll see.
Yeah, thanks super stealthy.
Okay, they're
feel free
looking
to
at
come
the
any other
days,
week.
age, year, temperatures, and those features goes that.
Yeah, come on, manifolds.
This is always resting in the fact that them knowing that those are actually those manifolds. I mean, it could be wrong, but I think it's probably right.
But they
But
say they find it in unsupervised way, so how do they do that? Yeah.
I think you can. That's another part. Finding a supervisors. I think that's after this. Here they have some manifolds that they found earlier, and they are testing how the models detect them, like how the Sparse Autoencoders like features. Features style manifolds local detectors. Sparse Autoencoders do not capture manifolds compatible. How do they represent them? Fix 5 contains special operations or activations with particular reconstruction using case number features. Middle features reconstruct local patches of the manifold in a piecewise linear fashion, and the union progressively covers the full geometry. The results place current sparse encoders in the middle between ideas for capture and shattering. Huh. Okay. So yeah, they're saying that they're kind of capture some a bit and shatter a bit, or like probably around middle. I think it's kind of if they're taking average, it's not necessarily that. Oh, I mean, it's that they're looking at specific manifold, so. Oh, so yeah. So for days. Yeah. So I was not right because they're not doing the average on manifolds. They're picking some specific manifold and checking that one. It seems like it's kind of doing a mess. Uh, Okay. The geometry. Okay, so yeah, so if you do the whole icing thing, they're saying that you recover, or you do the icing thing on the Sparse Autoencoders, and you or recover these manifolds that they already knew were there. Same pipeline provides a novel manifold encoding epistemic concentric in scientific context. This seems also related to the
Same pipeline
lie thing.
synthesis, a novel manifold encoding epistemic uncertainty. Ooh. Okay. PCA. Yes.
Okay,
But
here's the unsupervised manifold discovery.
okay, let's see.
Recovering coordinates geometric objects que por JML yeah. Okay, so I think this section is so the reason why this is not the yeah the paper that they talk about, right? That they were talking about on Twitter is that this, I understand it, is about taking the manifold features and recovering manifold from them. Not unsupervised in an unsupervised way, but it's not unsupervised from the activations directly getting manifolds. Okay, so a natural starting point. This is the icing thing actually work better than just the simple thing of sign similarity or whatever. By the code similarity, the super work. However, under space capture, the atoms spanning manifold and spaces may be nearly orthogonal, and their tiling, atoms converting adjacent polynomial sections have similar decoded directions. Okay, that makes sense. Decoded geometry thus carries no privileged information about the manifold topology that favors collectively tile. So that's yeah, okay. Collectivization studies offer a more principled alternative. Features that jointly represent a manifold fired together. In the setting case, the features that jointly represent a manifold have extreme variation against each other. I mean,
Oh.
I guess they only fire together if they are close, right? And you could have yeah.
Like this reminds me of the physics model in I think it was in the geometry of manifold, where you also have like features which are like repelling and attracting.
Yeah, although that was
Yeah.
about the model putting things in a manifold because it wants them to be separated in when they are be close, then when they are close, and separate when they are separate. And this is kind of inverse on that in some sense. Because this out once you have the features, then the ones that are close will fire close and will fight together, and the ones that are separate will separate together. And
Yeah, makes sense.
but this is yeah this is related to co-activation. I can think there is some reasons why it not me always the case. I need to think more about this, but it feels like
You compare 5 simulated measures. Oh my god.
this is feature activation like do you like if you have you don't really have I guess it depends on what you are uh, only if it's styling, only if it's you know compact, because like how much increasing one increases the others. I need to think about it. It's not obvious to me. It's always the case that you have that
If they
things
are
are the same.
correlated and you sample globally enough, then that makes sense. Like
But
you can
are
sample locally when
are things on the
oh,
same manifold necessarily correlated? Like you could
like
imagine different points being.
if you sample globally enough, I think so. If you sample, you can sample like the idea that I'm thinking of
I
is
guess they
that I
are.
don't know,
Yeah, they are. Like one is they're correlated with the near one, and
like
then the near one is correlated with the near one.
okay,
Yeah,
so
so
yeah, like for math concepts, I don't know, like you can have a set is very it can be very correlated if you sample only with like a group or something. If you sample only group theory text, but if you sample uh I don't know, pure set theory that's not in algebraic structures or something, set will be there, but it will be completely anti-correlated with group. So I don't know. Maybe that was the yeah the point you said you was also making. I don't know. Uh,
I don't know.
So how they correlate with each other is dependent on the exact thing that the exact data points that you're sampling and getting activations from.
So they try different. Okay, so they try different methods of checking similarity, and they find that the icing couplings and conditional coactivation reach the clear separation. Okay, so also conditional coactivation. I feel like icing couplings is related to conditional coactivation by the explanation on the Usagi thing that Claude did. But yeah, I feel like I need to learn more about that. Maybe ask Claude more.
Like yeah, what I'm trying to do now is just going where the math starts. I just every single definition, every single variable. I don't know, just googling it basically or clouding it.
Okay, so yeah, this is here. I'm kind of okay. So this is the end of the paper. This is nice as a way of testing. So this is not yet a method for finding manifolds in general. Although I don't know, feels like they should be able to. What is the bottleneck here on just not finding? Finding hundreds of manifolds in the models from the Sparse Autoencoders. Like yeah, it would be better if you had some method that unsupervised just from the derivation directly finds manifolds. But
Can you
why
say again your point?
why I'm curious what's the bottleneck for why this paper has like an example of manifold. Uh, of manifold that they found using the icing based discovery pipeline, and it's not like we use this pipeline and we found like 300 manifolds in the model. You know what I mean?
Can you try to rephrase your point or say again?
Why they didn't like what's the bottleneck for just finding hundreds of manifolds in the model
Oh,
using this method?
more compute. I don't know.
Yeah. I mean, I guess there is the labeling part of this manual, but I don't know, seems like it should be easier to find more, maybe. But yeah, I don't know. Like if we maybe I don't know if they have code or not, but if we just go apply their stuff and run it on the models, can we find another manifold? And if no, why not? Is the question.
Mm. Yeah, that could be done.
Because it's not like the other stuff was supervised, so you didn't require coming up with some idea of something that might be represented as manifold. But this should be just basically doing clustering on automatically on Sparse Autoencoder features. So yeah, new science. So that's basically it. I wish we can look a bit to the appendix, but I think we mostly finished now. I guess people feel free to talk about your takes on the paper and all that in general, if you want.
Yeah, I'm not really gonna
Otherwise,
go through the math
yeah.
in more detail though.
Otherwise, I think the thing to do now is like, yeah, maybe I we need to. Maybe I'll end the recording, or maybe not. I'm not sure, but I think people don't have takes now. I think maybe we just can spend some time trying to understand
I
the
had a
math.
question. Like,
Hmm?
can you
So
scroll up?
Yes. Which
Uh,
page?
so it was from a yeah. You have to scroll up a lot actually.
Yeah.
Mm, one of the figures, I think.
Wait. Is this one?
Yeah, I think this one. Yes, yes, the one with
Okay.
sparsity. Yes. So I think they mentioned that. Okay, can you scroll down a little? Yes. So they mentioned that at low k, atoms are broadly shared, and the manifold is shattered across unrelated groups. So is this like an example of superposition? Because like the groups are unrelated, but the shattering is done across groups. So do they mean are they saying that
Okay.
multiple groups are involved? Is that what they mean to say?
Okay. So you're talking about the B then, right?
Yes.
Okay.
At low
So
K, the low K regime.
yeah.
What does it mean exactly?
Atoms are broadly shared, and the manifold is shattered against unrelated groups. Okay, so uh,
Specifically, I also like it's also unclear to me what an atom means. Like, could you explain that?
okay, so I think atoms here just means in the Sparse Autoencoder just means the features, right?
yeah,
Uh, they're just talking
Yeah,
about
I understand what a
atoms.
feature means in an SAE, but like, how is an atom different from a feature? So
It's
like,
just a
I think
what I
it's
feature,
a
but
understood is
synonym
in
that
here.
this
what I
fancy.
understood is that the atoms have something to do with the decoder in the SAE.
I think it's just the light of the feature is just it's a more general term where it doesn't
Oh
have to
yeah, no, I
be
think you're
feature
right
in
about
essays.
the decoder. I think it's the atom here is talking about the like the direction of the decoder for that feature. Yeah.
Okay.
Uh, so they're saying that. So they're saying atoms are broadly shared. I think that, okay. Okay. So manifold shattered and across unrelated groups. Uh, Yeah, I'm not completely sure what that means exactly either. But okay, so you have log k. So we have a lot of sparsity. Let's say only three features or whatever. Uh, I guess if you have more. Manifold subset. Okay, I think you have low k. I think I understand. If you have low k, you have a bunch of manifolds. It's just saying that there is like few enough features that the multiple manifolds share a single feature. Like this is the regime where it's here, like where you. I'm guessing it's like where k is one or two or whatever.
Okay, got it. I think
So like
I
you
think I
have
need to read up on
very
some of these
few
concepts.
features, so you can't represent different manifolds with them. So you just have some feature that points to different manifolds.
Right, got it.
Because so it has to be very low because they say at intermediate K, and it says about compact set of atoms spans each manifold thing, and here that K is like 4, right? So that means they mean this part where the support is low, so it has to be basically 1 and 2 and maybe 3. So probably like 1 and 2. So of course it makes sense to me that if you have K2 in some top K SAE, you are not going to have representations for all of for each manifold because you basically barely have any feature like have very high sparsity, so you have to represent a lot of the activations in basically combinations of two features. So you have like more than two manifolds. You are you can't like it's not possible for you to represent them.
Got it.
Like I guess it's even less than the like it's even less than the ambient dimension of a lot of these manifolds. So anyway, anyone else has anything to talk about or ask or whatever?
Maybe if anyone wants to say some more high level, as in, do you see future in this unsupervised manifold discovery for Mech Interp more broadly? Because I personally do, but I think it should be generalized to also non-continuous manifolds. I'm not sure if there's a term for that.
Is that? I mean, is
Set of
that?
manifolds.
I guess. I don't know how to call
Non-connected
that.
set of
Like
manifolds.
maybe it turns out you can just can't think of that as just a bunch of separate manifolds, right?
Yeah. How they said it, non-linear. The thing that I really liked.
Yeah, but
So a set of potentially disconnected non-linearly curved geometric structures with causal
yes.
efficiency. Oh yeah, that is general enough for me. It is so general that it might be
I,
unquantifiable.
yeah, I guess, but if it's, I think
We are getting into the
like
free
there are
differential
reasons
line.
why you
Go ahead.
since you might expect things to be locally linear for that. There's a bunch of machine learning reasons why people say that it might be like locally linear. So like you uh, maybe can expect things to, even if it's actually like that, to decompose in a bunch of linear, you know, uh, manifolds, the same way that the manifolds decomposing a bunch of lines of like linear lines. It's not lines. It's like they call them rays, which I think is makes more sense because like it's not like the thing that the linear probes do are like the probes do are like one-dimensional manifolds because that's a curve. It's actually more specific than that. It's like some direction starting from the origin and going to the well, it doesn't necessarily from the origin because it have a bias, but yeah, some direction on the space, and it can't be a line that's like not uh, on that. Like you can imagine some other curve or line or whatever on that on other direction in the space that's not a direction from there. I don't know.
Hmm. Can you try to
I'm
repeat
not
that
sure.
point again,
I need to
please?
think more about that because I'm not sure I was saying it's
Okay.
completely sensical.
Wait, platonic something they said? If you scroll up a bit.
Oh,
Platonic
platonic
representation.
representation. I
Hmm.
was going to scroll a bit through the appendices. There is something interesting, but
Ooh, this is an interesting section.
Compare length features. But do they mean here different Sparse autoencoders on different models, which is, or do they for the same model?
I guess they mean the same model because otherwise it makes no
Yeah.
sense to say the same manifold.
I mean, you could when I think when people talk about platonic something, they usually they think they are not using it the way
They
other
usually
papers
mean
use it.
different models, but
Yeah,
they're studying the same model in this section.
yeah, that's sad. I think there will be something interesting of looking if you. I think you probably find the same. They tried on different models, and I'm assuming they don't mention something like we didn't find the colors were shaped on this way. I'm assuming that that I don't know months is always a circle in all of the models, so there's probably something to be found there, but I guess it's not the thing they're testing here. Eso trae muchos Sparse Autoencoders. This other similarity. This similarity does have ones on the diagonal. Similarity, co-similarity, geography, co-similarity patterns. I see. Variety of comparative geometry. Cosetas direction. Cosetas points. The sample armas for. Oh no, math. Are you reading this, Burnie?
Yes.
Nice pictures though. But no idea what a Viriatoris Rips compression motopy equivalent is. But okay, nice. Points make the shape. I mean, this was so we were talking about earlier about unsupervised finding of manifolds. Do they? Don't they like? What about the neuroscience people? Do they do that on the brains?
I'm not sure. I don't know.
Maybe I need to
Maybe
ask Claude.
maybe we can extract their knowledge. Uh,
Are there no? But if that's the case, why are there no more like? There should be at least a few neuroscience people getting into Mech Interp now, be like, oh, we could just do this. Why is there not enough that? Maybe they just already a lot of the 16 insights were already here, but I don't know. They have manifolds. For instance. Etcetera. Después the coders and spread more services. Okay, so this is basically just testing if the other thing is just testing if you can find some set of directions that captures the that explains the variance inside the manifold. It's not a measure of like there could be more that do other things. Like you could have more than one feature, but as long as it's actually already doing the thing that has the correct ones, it still has high on this metric, I think.
Okay.
I think that's most of it.
I'm teaching someone how to read math instead of reading the math in this paper app. So I will stop doing that, and now I will read the math in this paper app. Okay. Let's go.
Okay, I guess that's okay. So I think yeah, we can. The main paper
Yeah.
thing is done. I guess we now can get to the part where Burnie spends a lot of time reading the math and trying to understand it. But I don't know if we should record that or take the reading group percentage by now. Um, uh,
Yeah. I might also now check some application before going deeper. So maybe.
okay, yeah, maybe we
If
can
I,
just end the reading group here then.
yeah, but
It's
if
also
I
will also
go
be.
through the paper in detail, I can additionally record something and potentially post it on the YouTube channel.
Yeah, you can do that if you want.
But that's assuming I will go through it in a lot of detail, which because of other things I have to do, I'm not sure I'll do that in full comprehensive way. But I really want to.
Okay, yeah, I think we can get it. If you want to do that at some point, we can just you can feel free to record it and send me the video or something. I'll post it on the YouTube.
Yeah. I think I'll first now do some application though, because
Okay.
deadlines. Haha.
Anyone else wants to comment something or do I just end the recording now? It's been going for 2 hours, which is the typical reading group time these days.
That's actually, I think, lower than the average, actually.
Yeah, probably.
Yeah.
I mean, we are not the only
Oh,
ones that
Alpha
take
just
that
joined.
take that long. You see for example, it's looking at the machine learning street talk and on the Yannick server. They also 4 hours.
I'm basically right now trying to teach someone the machine learning street talk how to read math in papers. I need to stop doing that and actually read the math in this paper instead. Why am I so sniped constantly? I don't know. Whatever. I have to revert
ADHD is the answer, but
I have
yeah.
to do mechanism interpretability on my psychology because whatever. That is a rabbit hole. Yes. So
Yeah. I guess nobody say anything, so I just stop the recording. Yes.
All right. Thank you, guys.
Goodbye.